All right, are we live? Hello and welcome. Howdy. Here we are, serialize and deserialize a binary tree. Hard. So this one, I think is probably, this is one of those questions that are like, you kind of can do whatever you want. There's another LeetCode problem here. I already have it open. This, like, there are sort of quote unquote design questions that you have on LeetCode, and so hello and welcome back. There's kind of like design questions on LeetCode where like the question itself, you technically can kind of submit whatever you want and it'll be correct, some sort of something like that. You can kind of hack the problems in some sense. Like that's not really hacking because there's no real like challenge. I guess there's like a degenerate answer that you can give and you'll still get it, still technically submit it and get it correct. These are more of like, they're like design questions, but more micro kind of design questions. Like how would you design this specific, very specific, small kind of use case thing? Yeah, so in this case, like for quite a few of these are like, they have codecs, they call them. So like another example would be like, how would you compress a string? Or like how would you design, another one was like a tiny URL. How would you design a tiny URL? Which is basically you have like a URL is sort of like a whole sequence of characters and could have could be quite long, and then you want to make it to actually a very small, string that represents the same URL. Like how would you design that? Like they're calling all the kinds of these questions on LeetCode, which I appreciate them, but they're also sort of I don't want to say they're disappointing, but they're like you don't you kind of, it's almost like you don't get credit for not for solving it because like you can kind of come up with whatever you want. It's like they're really just to kind of get you thinking more than anything else. So serialization is the process of converting a data structure or object into a sequence of bits so that it can be stored in a file or memory buffer or transmitted across a network connection link to be reconstructed later in the same or another computer environment. Design an algorithm to serialize and deserialize a binary tree. There is no restriction on how your serialization, deserialization algorithm should work. You just need to ensure that a binary tree can be serialized to a string and the string can be deserialized to the original tree structure. Clarification. The input-output format is the same as how LeetCode serializes a binary tree. You do not necessarily need to follow this format, so please be creative and come up with different approaches yourself. Yeah, pretty interesting. But basically you get a tree, you get a string, and then given that string, you recreate that same tree. So there's like there's like a like a not a joke, but like because this program is being run on the same machine, like these serialization, deserializations, you can pretty much always like save this tree locally in memory, and then when you deserialize, you get the tree back, something like that. Yeah. Which is like not really the intention of the problem. The idea is that you have a string, and that string represents a tree, and then when you deserialize that string, you get the tree back. So, pretty interesting question. Number of nodes in the tree is between 0 and 10,000, and the node value is between -1,000 and 1,000. Excuse me. So I don't know how I would do this exactly. I mean, the way they serialize it's kind of interesting. So you can actually, if you wanted to, you could use their format directly. In other words, turn this into a string, which is kind of fun. So I actually really like the way that they serialize and deserialize their trees. I couldn't really think of a better way when I had thought about it in the past. That's a clarification. Yeah. It's, the input and output is the same, so they're basically saying, don't just use ours. You can come up with your own, you should. Yeah, I hadn't really thought of a better way to serialize and deserialize a tree. I thought theirs was pretty good. I think maybe a better way is to, you could do, Because what do they have? They have, the way they did it is kind of interesting. It's a pre-order traversal. So here's the head, here's the left subtree, here's the right subtree. It's not a pre-order traversal. I'm sorry. They did it they did it in a way that I think it's a little bit better than like a pre-order or post-order. But you can actually make this a little bit more compact by using like a tree traversal, like a pre-order or post-order. I actually think what's better would be like a level order traversal, which I think is actually what they have. Yeah, they actually have a level order traversal. That's what they did. Okay, so they do 1, 2, 3, null null for these two, and then 4, 5 for the next two. And then if you had like it would be null. Is it level order? Actually, I don't know what they did. I could be wrong about that. Null, null, and then let's do 6, 7, 8, 9. Okay. And the visualizer doesn't really work for more than one. Okay, no, it's not. It's not actually a level order. I actually don't know what they do. I really took the time to figure it out. Let me do this. But this is an interesting question, certainly. Definitely. Okay. What do we get with this? Okay. What if we put another null here? Six. Okay. So it's not a level order traversal, it's something else. It's 1, 2, 3, null, null, 4, 5, and 6 starts at the leftmost part of 4. I thought for the longest time that this was, I think it is the level order traversal. I think that's what it is. It's 1, which has 2 nodes, 2 and 3, and then those have 4 potential children. The first 2 are null, and then 6. So if you do 6, 7, 8, 6, 7, 8, 9, then of the children that are possible, so if you say null, null, 8, 9, it'll take the children that are possible. Okay. There is another way to do this where you say, you basically say, like, it's not as compact, but it's like, as if you had a full binary tree, like a full tree, every index would get a value. So like you could make the whole left of the side of the tree all null values. You'd have a lot more null values for that. But you can have an array of basically some power of, it would be roughly a power of 2. I think it's a power of 2 minus 1. I think it would be the size of the array. And then you can specify directly at the indices whether or not a particular node is null or not. The problem with that approach is that you can have things that are quite incoherent because you might have null values following, you could have values that are not null following something that is null. So you could have like, okay, this is supposed to be a child of the tree on the left subtree, but there is no left subtree, so it's just a floating node in the middle of nowhere. Whereas this format is a lot less incoherent because if you have null values, they're only going to be associated with spots that are children that exist. And so you're never going to have a null value underneath another null value. So this is a pretty interesting way to do it. I like the way they did it. I said, like I said, for the longest time I could not figure out how it actually was, how they actually did it, how it was actually used. It took me a really long time, but I actually didn't figure it out till now, really, and I never really took the time to just try to figure out exactly what it does. But it looks like a level order traversal where the nodes are children of some other node. So for 1, 2, 3 are possible children of 1, and then there's 4 more children here for a null, null, 4, 5 for this level, and the next level you have, since the first 2 are null, those don't have any children, but 4 and 5 have children, so you have 4 potential children, and then null, null, 8, 9 is from left to right what those children are. And it just keeps going that way. So again, we would have another 4 possible children for 8 and 9, and we can kind of, so if we did like null 10, null 11, right? And you have the left side of 8 is null, right side is 10, left side of 9 is null, right side of 11 is 11, or right side of 9 is 11. I'll make that 100. So that's pretty interesting. So I'm thinking if there's like another way. Like I said, you could do like a pre-order traversal, post-order traversal, in-order traversal, something like that as your inputs as well. Problem with a pre-order traversal is, and you don't have any null values if you do that. I think. The problem with a pre-order traversal is that it's not necessarily clear where the end of the left subtree exists. Like, why wouldn't it just be all of the nodes to the right of the first node constitute the left subtree, and then the right subtree is empty? I think you need more information to figure out where the bounds are on the pre-order traversal. A post-order traversal is similar. You don't necessarily, there's no way of really knowing how big the left subtree is. Now you could, if you wanted to, you could have a post-order traversal where it states how large the subtrees are, how many nodes are in that particular subtree. That you could have a pre-order traversal like that, but the problem with that is that, you know, then you have every node has an extra number associated with it. So you'd have 2 numbers at a time, and you'd also need to have, I guess, serializing that too. I guess you could have a different delimiter. You could have like 2 numbers and then a semicolon. So the 2 numbers would be separated by a comma, and then the third number would be a semicolon. You could denote it that way, and then if you did that, you could figure out, you could use a pre-order traversal, but that seems kind of wasteful, having all these extra numbers. You could also do, another approach would be an in-order traversal, where I like that one. I think you can go from an array of in an in-order traversal to the tree. But again, the tricky thing about that is, how do you know from left to right? How do you know what the which node is the head node? Again, it's like, how big is the left subtree? I mean, the left subtree could be the entire tree. Excuse me. Yeah, the left subtree could be the entire tree, and then there's only the last node all the way on the right is the head node. Left subtree from left to right is all. It could just, the whole thing could just be the left subtree, and the rightmost node is the only head node, only root node. And that could still be an in-order traversal, but it would just be Just so happens that your tree was, way bigger on the left side, and nothing on the right side. No right subtree. Yeah, so all those, the pre-order traversal, post-order traversal, in-order traversal, all those don't really have enough information to clarify how big the each portion should be. Excuse me. Or at least not in a single array. I mean, like I said, you could add the size of the subtree as more information. That would be sufficient. That would be okay. Another way would be, yeah. The problem with that though, like they all kind of have issues, right? Like if you do that, like yeah, you're adding more information, but also you have all these null values here that is also extra information. I think technically speaking, this could be, I think it actually is roughly the same size as the whole tree itself. So 3 minus 2, so 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6. Yeah, I think asymptotically it's roughly the same amount. The number of leaves is approximately the same as the number of children. The only reason why it wouldn't be, oh, I'm sorry, I'm wrong about that. The only reason why actually it should be way more leaves. The only reason it's not more leaves is that you don't need to specify the last level of leaves, so that saves you a bunch. But still, the number of null nodes is roughly half as the size of the tree. Yeah, so the number of nodes in the bottom level is, so if we added all of the bottom levels, those nodes should be all the null nodes. So should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Excuse me. Let me just count again. Yeah, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 nodes, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, there are actually more leaves, more null leaves. It's just the last level we don't show the null values there. So if it's a full tree, then this would be totally compact, right? The last level would be all the null values that wouldn't be shown here. That's interesting. But I guess what I'm trying to say is otherwise you would have all that extra information anyway for all of to specify all these null nodes. Obviously. Excuse me, yeah. All the null nodes you would need to specify use quite a bit of information in general. I guess my next question or questions would be, so that's interesting. It's not super compact until you get to the bottom level, and then you don't need to actually express that as all the null values. In those cases, this serialization has a boost in terms of the size. So that's level order. There might be pre-order, post-order, in-order, level order. Is there any other way to go through a tree? That might be better. I don't know how creative I could be with this. It's probably something really crazy in the discussion. That's pretty good. But I'll kind of ponder, see if I get to come up with something on my own here for a moment or two. What's interesting about this serialization and deserialization is what's peculiar is the actual representation of the tree internally would have a left tree and a right tree, left subtree, right subtree, and an initial value. And so you could, if you, I guess, like you could like create a hash number, an ID for every node, and then have a left and a right value which represents the some other hash ID in the tree. And if you did that, then you could just specify all the nodes in whatever order you want. And it's kind of like a graph. It's almost like a graph algorithm, something like that. The problem with that, though, is that every node would have 3 pieces of information now. And so now you're way more, now you're using way more information. It's a little easier to parse, though. It's definitely easier to parse. Yeah, but you would also have to need to generate these different hash IDs for every node, and then also, which is like a lot of extra effort, I think. Yeah, instead of just giving you a string that has an implicit order and the data associated with each node. Give all the nodes a new give all the nodes effectively a virtual memory address, quote unquote virtual memory address, and write the ID and the other 2 IDs, the left and the right nodes, and make a list out of that. Could do it that way. That would work. I don't think it's good, but it works. Excuse me. I like the level order traversal. I'm trying to think of some other ideas. I don't really have any other good ones. Yeah, the one I just described is sort of similar to like what you might do with a graph, where you might have sort of like an adjacency matrix, where with a tree, the adjacency matrix is pretty much just the 2 children, and that's it. Excuse me. Yeah, it's directed too, somewhat directed. Can I come up with something that's at least not better, but comparable to the level order traversal? Actually, yeah, I could. So what we can do is we could say how big the subtree is on the left or the right side, how big a subtree is, and then if there is no subtree, or if there are no child nodes, then we can just say, we can just leave it blank and assume that the subtree is just size 1. And then we could avoid writing any, and we could do a pre-order traversal doing it this way. And then we can avoid writing any null character, null values just to represent a null node. And we also, that saves us quite a few characters, right? Each null node instead of those 4 null characters. So yeah, so we'll have each section will be broken, each node will be broken up with semicolon delimiters rather, and then commas. If you see two commas, will give you the data, and then the size of the tree. And then if it's it's a leaf node, it'll just have data. It won't have the second part. And then we can use a pre-order traversal. Would probably be the simplest. So you can split, count the semicolons. I suppose you could take the entire sequence of characters, split on the semicolons, process each piece as its own node, create a node for each in an array of nodes, and then create those nodes on the heap, right, those pointers. And then using the array, you can sort of recursively, you can recurse through your range through the array that you just built to recursively reconstruct the tree. I'll kind of show you what that looks like. It's not easier to, maybe it might be easier to code than explain, or I could spend more time explaining. So yeah, we go. 30 minutes, not too bad. I mean, like I said, there's the discussion is probably more interesting than my own thoughts on this one. What we can do is, as I said, we can use, so the format will be as follows. We're going to use a vector. Actually, we don't need a vector. We can do I guess vector is fine. We can use a vector, and we can use another item here, which is the string we're going to use here. And I'll explain what my idea is. So code a pre-order traversal in which each node separated semicolon, and the node has one of two values, or two values. The node has two values separated a comma, has 2 values. Then node, internal node, first value data, and the second value, excuse me, is the size of its subtree, size of the tree rooted by itself, rooted by it, or for which the node is the root, represents size of a tree, tree in question, subtree, rooted, given node. Given node has 2 values. Tree in question is the subtree root of the given node. If the given node 1 value and the node is a leaf node, any children? I don't know if this really works because this might not actually work the way I'd like it to, because how do you represent an empty left subtree? Even with this approach, I don't think it works, because if you have an empty left subtree, the next node, the next node is, or the next nodes for a pre-order traversal, you would expect, the next 2 nodes would be, the first node on the right would be the head of the left subtree, and then further down on the right subtree's head. The problem with that, though, is what if you don't have a left subtree? Excuse me. I guess you could just have a, I mean, you could do the same thing with you can make the same kind of optimization with the the level order serialization. You don't have to write the whole null value. You could just have an empty comma, just emptiness between the 2 comma values. So I guess you would want to have an empty subtree, which would have no values, nothing in it at all, and that represents an empty left subtree. Ooh, excuse me. Well, if you do it that way, maybe that's a little bit easier. So you could say the head node is the first value. Now, if there's an empty semi, we could use colons or no commas. There's an empty. There's nothing between this next comma. Then that's an empty left subtree. Otherwise, you take the first value you see, that's the head of that subtree. and it just kind of keeps going. And I guess you would. No, the problem with that though is how far. Yeah, I guess you could represent each missing node as or each, like, not just the leaf node, but an empty left subtree, empty right subtree, as just a comma, just two, a comma without any values between the two commas. So eventually you get to a left and a right, left node and right nodes that are null, becomes a leaf, and then the next value would have to be the previous node's right subtree, head of the subtree, and then the next values would start from there. So if it's two more, or if it's even just one more empty comma, then again you go up one level again for the next parent, previous parent. So you don't want to use a stack to figure out which parent you're operating on. So as you traverse down, you add these parents. Thinking of both for the serialization and deserialization, what those things are going to look like. So serializing, excuse me, yeah, you would. You could do it recursively, right? Quite literally, a pre-order traversal that if it's empty, the node, then you just have a comma, and if it's not empty, you would have the data written and a comma. As an integer, and then I guess you could do that. Do a pre-order traversal, and then to process the pre-order traversal, you would kind of have like an iterative. Well, I guess one issue is like, how do you figure out when the excuse me. Yeah, I guess it is sort of an iterative process. Yeah, because you don't know. Okay. Go through the pre-order traversal using a stack. Yeah. Seems okay. Excuse me. Yeah, I think you just need the parents on the stack. That's all you need. Once you process the left subtree, and you pop to the parent, then you'll see so when you see a right node that's empty, that's when you pop to the parent, or you jump to. Yeah. Yeah, I guess you push each node you're working on onto the stack, and then that's the top of the stack that you're operating on. So then once you filled that node, you pop the stack, and now you're processing either the left or the right side of that node. I guess first you process the left side, then you process the right side. So I guess you just, on the stack, you just need to keep track of which node you're working on. So you just push tuples. Or better yet, push a struct and then update the struct. That's better. Yeah. That's pretty simple. When you pop to a root value, that means it's the left side has been processed. And this next value you're looking at is going to be the right side of this tree. And when you pop a value, when you've processed the right side of the tree, that's when you could pop. So if you pop up to something that you've already processed, you're looking at the right side, then you can pop that too. And then once the stack is empty, then you're done. That's interesting, yeah. So a pre-order traversal can work. That's kind of fun. Let's do that. That's not too bad. That's not too bad. All right, so we're actually not going to use two values. Pre-order traversal such that a value if, so that each node separated by a comma if there is value between commas, i.e. an empty string. Then the given node is a null node. It's an empty node. Yeah, so we can do it that way. Okay, let's try this. Empty string, and we're gonna say const auto. We're gonna do this recursively. Who's gonna DFS? Actually, better would be pre-order. And we're gonna say tree node R, const auto F, order. We want access to ret. Return ret. Pre-order of root pre-order. And we're going to say base case. Say if not ret or not R. Then we say ret plus equals a comma. Otherwise, say ret plus equals R value. That's going to be integer to s, or to string rather. And this is just an integer. And then we say ret plus equals comma. And then that's it. That's all we do. Oh, no, excuse me. F of R left and f of our right. Process the left subtrees first, then the right subtrees. So we can pre-order, get our pre-order string, and then now we can say we're going to use a stack. And say stack of tree nodes, st. We're going to say while, and we want a current node. So we're going to say current, start off as the null pointer. So while the stack is not empty, or current is not a null pointer. So as long as we have something to process, and we start this off at, or actually, so this is kind of tricky. How do we want to do this? Don't actually want to do it that way. We want to take a look character by character. And we can do int temp equals 0. And I suppose what we want to do, we actually want to parse integers. So we want to say, like, what I think a better thing to do would be actually to parse out an array first before we reconstruct the tree. You can actually do these in tandem, which is probably what we want to parse and reconstruct the tree in tandem. In tandem. Yeah, we probably want to do it together. No real sense in creating a vector of integers first, but we really don't need to do that. So take each character and we'll say if, so we can kind of use like a state machine type of thing. If the character is a comma, then end a previous sequence, I guess. So we would say int I, or int previous starts off at 0, and we would say unprocess the node. So we would say string x is going to be data.substring of previous to I minus 1, or no, excuse me, to I minus previous plus 1 minus 1. So not including the comma. So there's some previous, it's previous plus 1 to I minus previous. Yeah, so we're not including the previous comma. I guess the previous comma initially would be like -1. Not including the previous comma, and also also not including the current comma. Right, so it's going to be the values between these two commas. Now, the tricky thing about this is I don't know if there's a way to really specify this, because you could have, if I and previous are equal to each other, so in other words, the first character is, see if the first character is a comma. Oh, we can say it's the size of k. And I guess we could just say if k is greater than 0, then this is what we'll do. Otherwise, do something else. Previous actually should be 0, I think. Is that right? I think what's awkward about using previous values is that you need to, like, there's a point where it's not set, and then you have to set it initially. Let's see, how can we do this? If the first value is a comma, we can make that an edge case. Yeah, that's a null pointer, right? If you're just empty altogether, or if you have just a comma. So it's guaranteed the first won't be a comma. That means we can make the previous could just be -1. So if we saw a comma at position 2, which would be typical, right, like 5 comma, so, or position 1, then we would have 1 minus previous, which is -1, is +1, gives you 2. Oh, that's interesting. 1 minus -1 +1 gives you 3. Excuse me. Yeah, okay. Yeah, so it's actually -1, because you're not including the previous comma and the next comma. So k is I minus previous minus 1. And that's k. And that could be 0. So I think that we actually do handle this case correctly. Come back to that. And then we just say if it's 0, what happens if we try to take a substring that's 0? We could just test it. I don't know what this is going to do, by the way. I forget that frequently. Oh no, oh yeah. Oh, okay, that's interesting. So it does give us an empty string. Doesn't give us an error, which is what we was hoping to not see an error. There we go. Yeah, that's what we want. Okay, good. That's kind of the behavior I would expect for the substring. Okay, nice. So yeah, we could just say k previous of I plus 1, previous plus 1 k. Previous is going to be set to I, and we'll say process the node. We'll say constant data or val. It's going to be string to int of x, and then we can create a new tree node, new node, and it's a struct, sure. Equals this value. This new node. Left is a null pointer, right is a null pointer. Those will be. Yeah, I think it's probably better to use the value left and right. Let's do it this way. Now what we want to do is take stack top, which it shouldn't be empty, the stack. It won't be empty, or can't be empty. It could be empty, actually. We can do it this way. We'll say if st is empty, stack is empty, then stack is not empty. Let's do it this way. So let's make current the null pointer. Stack is not empty. Update the current to top. And we'll just say parent. We'll do it that way. So parent. And you could say root or ret. And we'll say if the stack is empty, we can set the parent to the top. If it is empty, we're going to set ret equal to this new node, and we're going to push this new node. It's not empty, we can set the parent to the top. And we're always going to set the previous to I. What we're going to put on this stack is, we could use a tuple. We could put a tuple there. I wasn't sure. Actually, you know what's better? A pair. A pair is better. And I'll explain in a minute why we want to use a pair. Yeah, we could use a struct as well, but I'm not going to go through all that trouble making a struct. A pair should be fine, because you can modify a pair. That's what we want to do. So we want to say, we see a comma, and our previous sequence and process the node, and we're going to take k is I minus previous minus 1, previous starts off at -1, previous plus 1k, get that value, convert that x to an integer. We have our new node, create a new node. Now we're going to get the parent. Now if the stack is empty, then we're going to push our node. That's going to become the root of kind of everything. If it's not empty, and we're going to push make pair, and this is going to be a new node, and the left subtree. So basically, true and false is going to tell us whether or not the left subtree has been fulfilled yet. So it's going to be initially false. We haven't fulfilled the left subtree. The parent, and we're going to say left filled, st-top second, and we're going to say boolean left filled. Will just be initially false. Parent is going to be the first of what's on top of the stack. If the parent exists, then we're going to say parent left, and we say if left filled, so what's interesting here is if the left is filled, we're going to do something special. So if the left is not filled, the parent left is going to be set to this new node, and we're going to update equals true, right? Otherwise, if the left is filled, that means we're going to say parent right is this new node, and we're going to pop off the parent from the stack. So we take this parent and we set the right node to be the node we just created, and we pop that parent off the stack. Yeah. And what's interesting about this is so the left side of this node is now considered filled. Okay. On the stack once we add this new value, and we're actually going to push this node onto the stack, this new node, and keep processing it. So this isn't quite right, I think, this logic. I don't think this quite makes sense. I think this we push this node onto the stack kind of regardless. There are some things to check here, but the basic idea is that we have a new node that's going to be the head of a subtree. So we've got to push that onto the top of the stack and continue processing. But if it's the left subtree of the parent, so we're going to associate it with whatever's on top of the stack. We're going to associate that's the parent, and we're going to associate that parent with this node. So we're going to say it has a left, not filled, but left selected, I guess. Created or selected. So we already have a node for the left subtree. If we don't have a node, that means the node we just created is going to become that left subtree. So parent left becomes that new node, and we take this parent, we take at the top of the stack, which should be the parent. We set that to true, that we have a left selected node. If not, if this is a right subtree, that parent, we set that right subtree and for the parent, and we actually pop from that parent. So what's going to happen is after we finish processing this node or the children, the next parent is going to be another it's going to be further up the stack. So this parent has already gotten all of its left and right association set. So you can pop the parent, and then we're going to push the new node we just made. I think that actually is correct. I think that's all you need to do. And update previous to the right, to the correct comma. And then the next piece to look at here is whether or not there is a value in X. So if it's the empty string, we do things a little bit differently. We don't actually create a tree node at all. Yeah, so that's kind of interesting. Yes, so you're actually going to say, depending on K, you're going to do the following. So we can actually put this here. Say tree node. Or it's a null pointer altogether. If K is greater than 0, meaning that X is not the empty string, right? Then we can get the data and create a tree node out of it. Otherwise, we have a null pointer. And then what we're going to end up doing is we're still going to do the rest of this stuff with the parent. So the parent is going to get basically get a null child. And what's that going to look like? So null child, left selected. So these are the same. New node was a null pointer that goes to true. New node null pointer popped. Yeah, that's all the same. But we don't actually need to add. So if new node, then we can push onto the stack. We won't actually push onto the stack if it's an empty node. There's a lot of pieces of this, quite a lot of logic going on here. But this is how you process each node, and that's kind of it, actually. I think that's all you need. Is that it? I think that's it, actually. Believe it or not. I accidentally clicked VS Code here. Huh. Might be that simple. I don't know what happens when we do this. We do it on time. Oh, yeah. Okay. Done. There you go. That's my pre-order traversal, my post-order traversal, or my pre-order traversal. That works. Well, there you go. Yeah, okay. Sweet. I don't know. Let's try some stuff. Oh, it's only between 1,000, right? Negative 1,000, 1,000. I don't know. It's probably something I did wrong with this, though. There's always something that I didn't do correctly. Let's go for it. See what happens. There's got to be something that's wrong. Hey, it works. Sweet. Okay. Hey, we use a lot less memory than everybody else too. It's a little more involved, but less memory. I like that. I think that's good. I think that was a good way of doing it. That's pretty solid. Pre-order deserialization. We're slow though. We have a slow deserialization. Serialize and deserialize. I don't know. We use a lot less memory though. But how do we pre-order is kind of tricky. Well, we could do a pre-order with a stack. We could try that. How does that work? So it's a lot easier to do this pre-order traversal without a stack, but I think the way you can do it would be push. I think you could traverse the tree the same way we did it here. Push the node onto the stack. Process that node. Push the left node onto the stack. And say on our parent, we could push the parent with also a Boolean or the left or right Boolean and say that we've processed. Yeah, by the way, this is actually, this is kind of interesting way of traversing a tree. This is special. This is a pre-order traversal, and you can modify this. Instead of using a Boolean, you can use an integer. It's a pre-order traversal of any. You can change that Boolean to an integer, and this will be a pre-order traversal of any a tree of any size. Believe it or not, a tree. Let's give you a pre-order traversal of a tree of any branching factor, any arbitrary tree. If you just change this pair from a Boolean to an int. And so instead of a left selected, you have an integer. And it tells you, here we said false means that we didn't process the left side, or we didn't select the left side. True meant we did select the left side, and now we have to select the right side. And then if it was true the next time around, actually no, once you've already selected the right side, then you could pop all together. So if you had 3 nodes, 3 children, you could make it 0, 1, and 2. So if you saw 0, that means you have to select the 0th node. If you saw 1, that means you select the first node. node 1, index 1, and then if you see 2, it means you're going to select the node at index 2. So you could make this 0, 1. So if you see a 0, then you update this to a 1, and then if you see a 1, you update it to a 2, and if you see a 2, you don't just update it to a 3, you actually can pop altogether. So you'd have 0, 1. Really, you would only be working with, really it would only be 0 goes to 1. You see a 0 go to 1, see a 1 go to 2, and then you see 0, 1, 2. Yeah. You actually have to have 3 different options. Here you only have 2 options. You only need 2 options, which is really false is a 0, 1 is a true. Interesting. Yeah, really interesting. So, okay. But yeah, you can pre-order Traversal any tree like this. You just have to modify the Boolean to an integer, and that'll tell you where you are so far in the tree when you're processing. This is also how you can modify a. This is similar to what you can do for a if you had a when you had to flatten an array, and the array data structure was either an integer or a flattenable, or a quote-unquote flattenable array, or nested array. If you had a nested array data structure, you could also perform a pre-order traversal of that data structure, nested array data structure, because it would create sort of a tree. You could do it iteratively this way instead of recursively. I think you could do a pre-order this over this tree too. Same deal. Just basically copy paste this code. I think that would be faster if we do it that way. I think that might be part of the deal. This is also another way to do. This is basically just a pre-order. So let me. So we're going to say not return, but we're going to have a string. And we're going to have, instead of I, we're going to say really just a while loop, I think. So while, and we're going to have tree node r equals root, or a for loop. I like to use for loops. And r, then it's updated. We'll update r within our loop here. We're going to say tree nodes, boolean, r is root, as long as you have an r. Const character c equals state of I. We don't need that anymore. We'll say we don't need that anymore. Process the node. So we can process the node. R val. Yeah, so we'll say ret plus equals toString of R val plus equals, and then left child or right child, select the next child. So we can say we don't have a previous substring, so node, new node, depends on the parent. So we would say we don't really have a new node anymore. We're not building the tree, we're just processing the tree. So we'll say left selected is false, or index really should be. So the stack is not empty. Then we're going to set the parent to be the top of the stack first, and index is going to be the second. Otherwise, we're going to set ret to new node or the root to the new node. We don't really have that. We don't need to do that. If there is a parent, and we're going to say if not index, yeah, so the index is false. We're going to set that to true, and we're going to set parent left equal to new node. We don't actually need to, so this processing, we don't actually need to do this. Or no. So what's interesting is, so the idea, let me think about the idea here first. So the pre-order traversal, we're going to process the parent node and then push the left subtree onto the stack, and then process the left subtree. So we actually want to push the right subtree onto the stack. Is that right? Well, you want to process what's at the top of the stack, right? Process the left subtree, and when you're done, process what's at the top of the stack, which would be the right subtree. So you process the left subtree and push the right subtree onto the stack. So it's a little bit different, I think, than doing what we did here. This is not the same thing as a pre-order traversal. This is just building the tree using a pre-order traversal. I don't know. I'm a little confused. Maybe it's not quite the same way that you would process what I said before, processing an arbitrary sized tree, arbitrary children, arbitrary branching factor. Let's see. Process the node, select the next child. So I think you do want to push this onto the stack because you want to return to it, right? So yeah, I think you do push this onto the stack. I think it's actually very similar to what I had before. It's just slightly different based on the context. Process node, push node onto the stack if, excuse me, trying to think if you would do, do you just push all the other children onto a stack? Or do you push them onto a queue? No, what you want to do is push the node itself onto the stack so that when you process this node, process the next child of the node. Does that make sense? I don't know if that makes sense either. I don't know. I gotta think about how this would work. What do I want to do? Process the node. Then going to eventually process the other children, but we want to process the left child. And after processing the left child, we want to process the next child of the parent. So we can figure out which child to select initially. So our index can be 0 or false. After processing, when we pop, that's when things get interesting. So if there is a parent, if there's no parent, then things are not too interesting. But if there is a parent, and so our stack's not empty, that means that there's a parent. Could set the parent to what's at the top and the index of the parent, and we say if index is 0 or not 0, that we'll figure out what to do with our parent. But what we're going to do is actually say we're going to update the values for our parent. So this will actually tell us what to update R to. It's going to be parent depending on the index. So if the index is 0, so that's kind of complicated. If the node we just processed is the left child of the parent, then we want to update the next node. When you reach that, when you get back to the parent, the next node you're going to go to is going to be the next child. Yeah, that's fine. And then actually, if what we're processing now is the last child, then we're actually going to pop that parent altogether. This actually doesn't tell us yet which node to look at next. Not necessarily yet. So if there is a parent, we're going to update this parent after we process this node. Not going to select the child. So update. Whoops. Update which node to select which child of the which parent process next upon returning to the parent node. Update which child, update the index of the child of the parent to process upon returning to the parent node. It's a mouthful. It's kind of confusing, but at some point you're going to return to the parent node, and so we're going to update which child to process when you return to the parent node. So the stack's not empty. We have the parent at the top of the stack. It's index at the top of the stack. And if the index is 0, we're going to update it to 1. If it's 1, then we pop the parent altogether. We don't have to process that parent anymore. If the So the new node that we're going to push onto the stack is going to be the left child. So if there is a left child, so what do we push onto the stack? It's actually going to be R updates to the left child. So what do we push onto the stack? Well, we could push the current node. Right? And then we say R is left. Does that make sense? So process this node. We'll suppose that we have already done some processing. So process this node, check the parent. We say, okay, we now process the left subtree, switch that parent now to the right subtree. We have to push this node on the stack, certainly. Now it depends if this node is a leaf node, then we actually want to go to the top of the stack. I'm going to go back. We don't process that node again, though. We want to go to the top of the stacks, the next child on the top of the stack, depending on the index. So whatever's on the top of the stack, go up to that node and take the child of that. That's the next node we're going to process. If this is a leaf, if we have a left child, then we can just jump to the left child. What you would do here is that you'd actually loop through the children that exist. So if there's no left child, you go to the right child. Right. Now it's interesting though. What's interesting is that we might want to process the. We actually probably do want to go left to right, or like cycle through all the children even if they're null pointers, because we want to update the parent. Parent's positioning correctly and pop that off the stack correctly. So actually we don't want to skip through children. We actually want to process all the children. So we would go to the left child. Excuse me. Maybe, I'm not sure. I'm actually not sure which child we go to. We'll think about that in a moment, but process node, it might not exist, so or stack is not empty. So or if that's not a null pointer, or the stack is not empty, we keep going. If the R is a null pointer and the stack is empty, then we're done. But we're either gonna, so we process our node, we say if R, then we take what's in R, if it's not null, stack is not empty, then we have a parent and an index. If there's a parent, can do things. And we say again if R, then we would push So if R exists, we're going to push that node and process one of the children. So now the question is, if R exists, we can just process start with the left child, right? Start with the 0 index child. If R doesn't exist, then we've got to update R to the index based off of what's at the top. So sort of index plus 1. So it would be st top. So if it's not R, that means there's something in the stack top, and it's going to be we have the index already, right? So it's if we pop the parent, so we just popped our parent. Now when we go up, so let's say we just process the right subtree, we pop this parent, we would go up to that, now what's at the top, and we say bool index equals, or just index equals top second, say if index. So depending on now what's interesting is the stack could be empty after this point too. Or the node is not null pointer exists. Next child. So the node exists, then continue processing on that node. I'll always move to the next child of a node on the stack. There's guaranteed to always be something on the stack. So even though you process, you're only going to do process one node at a time, one subtree at a time. When you pop, that means there's got to be another node above that has some other subtree to process. Yeah, it is possible. So now if this is actually where we exit, if the last thing we popped was the root node, so we processed the root node subtree, then we're done. Now one question is, I'm wondering if this needs to put this into a while loop, because the processing that we're doing here is, I keep clicking, I don't know why that keeps happening. The processing that we're doing here is slightly different from the processing that we're doing over here. I'm curious, so if you update the parent and you pop it, do you update the next parent? So you process the right subtree. No. You do that beforehand. So as soon as you start processing the right subtree, you pop that parent from the stack altogether. Yeah. So in the pre-order traversal, the root node will already be gone, or already be popped away a long time ago. So you only have to do one at a time. If there's anything left in the stack, then you would continue. So you would take, this will tell you which child of the root node that you need to process. actually, you kind of just do this whole thing again. And so here, if you have false at the top, then R can be R right. If you have true, or no, R could be R left. Not R. R could be parent left. Otherwise, R is parent right. Yeah, you only need, so it's only the left of the right. So if you haven't processed the left subtree yet, then you would process that. Haven't processed the right subtree yet, then you would process that. Actually, I don't think, so the left subtree, if it's a null pointer, then you would update this to the right subtree. And then here you would jump to the right subtree, and if that's a null pointer, then you would take the parent and now pop the parent, and then take the top of the stack and say whether or not you process the left. So what's interesting is I think the left subtree, I don't think you're ever gonna see this. I don't think it's possible to ever, in the pre-order traversal anyway, where the parent, the left child of the parent, trying to think about this here, where the left child of the parent, because you're doing a pre-order traversal, you're never going to be in a situation where this is false, the index at this point is false, when you reach this point down here. Because at this point you're going to set it to true if it is false. Yeah, I think this will never occurs. Will not occur. I think it's fair to say that this is a dead branch. Yeah, I think so. And the reason for that is just that because, like I said, because it's a pre-order traversal, you're always processing the left subtree before you process the right subtree. You'll always, every time you reach, when you finish processing a subtree, either left or right, you're either popping to something that has a right subtree to process, i.e. finishing a left subtree, or you're just finishing the node altogether. So you're never going to be in a position where you need to process the left subtree. But that's how you decide the next node to jump to. So I think this will work too. Could try it. So this is a pre-order traversal. You can use this stack and just stick the index of the node, like which child to process next, and on the stack, and then start off a pointer to the root node, and check if you either have a pointer to something or your stack is not empty. Then if you're not pointing to something, that means you're processing a child of a leaf node or just a null child. But if it is not null, then process the node. in pre-order fashion, and then you're going to update the parent that you did. If there is a parent, you did in fact process that particular child, and the parent knows which child is expected. It's being processed at the moment. Then you update the parent to index to the next child. If the stack's empty, then there is no parent, right? And you don't do these things. You set, if you have a node that you're processing, you're going to push that onto the stack as another parent, and say update to the left child, the first child of that node. If there is no node you're processing, so you're sort of at the end of one of the children of not a leaf node, but a node that doesn't exist. You're processing a node that doesn't exist. Then you're going to jump to the parent and use the parent to inform which child of the parent to operate on next. So you've totally finished processing a child of some node, some subtree at that point. Yeah, and I think that's it. I think that's the whole idea. I don't know if that works or not. I guess we'll find out. Now what's interesting is the way I've formulated this, you actually want to null nodes the null nodes will still be processed. Yeah, something like this. Something like this is what we want. Hey, oh, it worked. Whoa. Is it true? Does it work in all cases? Really? I don't think so. There's got to be some snag, something I missed. Oh, it works. Hey, check me out. Whoa. Hey, how you like that? So there you go. That's two different ways. So this is a pre-order traversal. So this is a way you can process a, by the way, there's array flattening, I guess it's called. That's kind of a classic question. I recently failed an interview because I tried to iteratively flatten the array as opposed to recursively flatten the array, and the flattening of the array would be more or less like a pre-order traversal. And I didn't do it right, and I should have used something similar to this. Use a pair of tree nodes and booleans as opposed to a tuple. So it would be more like a list of two values. It's a little different in Python, but in C++ you could do something like this. And so at the top of the array, at the stack, top of the stack, so you process the node however you're going to process it, and then you just want to get the parent as well as the index. If the stack is not empty, you can update the parent and index to what's at the top of the stack. If there is a parent, then you can update, modify the index for that top part of the stack. And then, so that means you process the sort of left tree, and then you can update. You know, if you have a node, if you are pointing to something in the node to process, then you can continue processing, right? Add that to the stack, and that's sort of where you continue on those nodes, and then start with the first child, right? Update to the first child. Otherwise, you're going to look to something on the stack, right? So if you just basically processed a null pointer or a null node, then you're going to look at whatever's on top of the stack and take a look at the child there, and this should never be reached, right? The children, if you're going pre-order, then the left child will always be kind of marked as processed by the time you get to this part, just because the code above will have done that if there is a parent. That's it, yeah, and then you just, so you go to the parent and go to the next node on the parent's next node, and process that way. So you could do pre-order traversal. And the interesting thing about this is you could change this Boolean to an integer, and now you can operate on a variable branch size, variable integer set for a tree. So this works on arbitrary trees, not just binary trees, which is pretty nifty. Pretty nifty. You could do a similar thing for an in-order traversal too, is that you can, I don't know if it's the same thing for an in-order. I know pre-order it's a little bit easier to think about, but post-order or in-order you can use, for at least for binary search trees, you can use, I think probably for arbitrary trees too, you can use like a threading. So I think I've gone over that. That's like a, the left subtrees you would set, all the left subtrees you would set the threads back to the parent node, and you just do that on each child. I think you just thread back to the parent as needed. Yeah, so to do an in-order traversal, you can use Morse traversal with threading. That's actually a little bit more memory efficient. And then if you wanted to do post-order, I think it's very similar to what we just did here. It's just the processing would happen after at the end. And yeah, I think you do the processing at the end. Yeah, I think you actually just shift. So if you put this at the bottom, what's going to happen is, no, post order is a little more complicated actually. I don't know. I've been thinking about that one too. Like, how do you do? This is a pre-order, but a post order is a little more involved. What you want to do is you want to actually process the. So what's going to be pushed onto the stack is you're actually going to push the results of the processing on the left side onto the stack, and then process the right side, and then use what's on the stack in your processing. That's sort of how the pre-order would work. But tricky thing with that is, like, how do you, or post order, excuse me, post order is kind of complicated actually. How do we do, so we have pre-order, we have in order, but how do we do post order now? I think you've got to store all of the results of each of the children in a post order. Like if you're doing a post order, variable size post order, you know what you've got to do? You do the same thing here, except this processing doesn't happen here. The processing actually happens, I think it would happen before when you pop the node. I think that's what you've got to do. You've got to have not just the integers, or excuse me, not just the index, but also you actually have like an array of each child's result. So when you finish processing a child, the result of that subtree would have to go into the array of values for on the top of that stack, on that stack top. So you have to save the values that you after you've processed them. So when you pop, that's actually the key. When you pop, you're going to actually process the node there. You're going to use everything in the stack up to that point, all of the values, that array of values, to process this node. When you pop, that whatever is at the top of the stack, if there is something, that's where you're going to save the result of that computation. So your computation is going to happen here. So you can say post-order processing would happen here. And the struct on top of the stack would need have the processing other nodes saved on top. Yeah, so you'd actually process the parent node here. Would happen here, and yeah, it's really interesting how that would work. Obviously, if it's an empty node, there wouldn't be any processing. Pre-order processing happens here. So you have pre-order processing here before updating the parent node. Post-order processing happens actually when the parent node, when all the other subtrees have been processed, then you put post-order process the parent node with all of the other values already set and saved. So you'd have a parent, an index, get your index, get your parent. I don't know what node you're looking at though when you're processing this parent. Like, I guess you'd have to be at a child. Like you'd have to have processed. Like let's say the last child is an empty node, right? The rightmost child is an empty node. Then you would get to here, and you would have the value. It doesn't have to be empty. I mean, it could be. Well, maybe it is empty. I'm not sure. Well, after processing each child, so actually at exactly this point here, when you pop. No, it's not. That's kind of tricky. I don't know. It's a little bit different with. I think post-order processing is like entirely different. I think maybe this doesn't work the way that I'd like it to. I don't think I could just stick it right in here. The reason for that is if you tried to post-order traverse, what's going to happen is what's today, by the way? I think today's Tuesday. Yeah. If you try to post-order traverse, what would happen? You would, if you go piece by piece, you would no processing here. Right? We would comment that out. Parent would be null. Index is null. Stack is empty. The stack's not empty. We're going to push this parent on top and set the index. Or no, excuse me. The stack is empty. Then there's no parent, and so we'd skip this part. Excuse me. And so R is not empty. We push R and go to the left subtree. Now we put an empty in array, push an empty array, and go to the left first child. That's fine, and process those arrays, right? Those children. But let's say we are at a child that we're finishing like a whole bunch of children. Let's say we're at a leaf node, right? And there's a whole bunch of children that are empty. Stack is not empty. We take a look at the parent. We set the index there, depending on which index we're looking at. So in this instance, so what's interesting is we actually don't process, we don't do the post-order processing here. And the reason why is because we haven't actually processed anything yet. The post-order processing, I think, has to happen here. Because we didn't actually process this subtree yet. I think maybe you can put the post ordering processing here, or maybe you could put it down here. Because what'll happen down here is, let's say we get to a leaf node and we have all null pointers. So we look at the parent, we say the index, and we update to the next child. Now, the tricky thing here is it is actually at this point where we would process the null node, right? So of the null node happen here. Yeah. So you would process that null child here, and you update to what the next node that you're gonna point to is going to be. What's interesting is I don't think you do the post order processing here, and I don't think you even pop your. I don't think you process this at all, actually. Post order process. Yeah, I think it's actually easier to think about it logically if you don't process. So I think both of these would be skipped in a post order processing. The reason why you would skip both of these is in a post order processing is that you didn't actually process the node yet. Like, you're not going to process it here, and you haven't processed anything here. So why would you update the parent to go to something else if you haven't even processed it yet? Now, it almost makes sense to do this, but the problem with doing this before you do the processing is that you don't have the return value to push to this top. So that parent node, when it's processed, is aware of what that return value is. So if you just start pushing, you start supposing that you've already updated that node appropriately and start moving through cycling through the indices, it's going to miss information, right, inevitably. So I think this part would be skipped, I think, altogether. So this would be commented out. This would be commented out. So you just have this portion alone. Where you don't do any processing yet, and you just keep pushing the node into the stack, nodes in the stack. Or if you get to the bottom, you would process the null node, whatever that might do, and update the top of the stack, which has an array of where it should be updated. Won't be reached in post order processing. This is significant. Okay. All right. So what else do we have? Post order processing of the null node would happen here, and the struct on top of the stack would need to have the processing from all of the children saved on the top of the stack. The struct would be updated here. Yeah. So this line would be used. Right, so if there's nothing in the stack, then we would just exit. If there is something in the stack though, you actually probably would do it below where you select the parent in the index, because you need the index in order to figure out where you're updating, what part of the stack you're updating. Now what's tricky is value So here's the thing. This is, if you process the null node, it would happen here, and you would update your so I guess what I'm curious about is, do you I guess what I'm curious about is I think you add a while loop here. Yeah, so something like this would occur if you complete a node here, then you actually have a while loop inside. So post-order processing would have a while loop inside here. Post-order processing wouldn't do these things. You'd have a while loop, so while the stack is not empty, you would set the parent, set the index, and then compute the results, and push those results on top of the stack. And if the index that you found, when you update the index to the next child and update the so you would update the results, update the parent, go to the next child. If the index that you're operating on is the last child that you update, then you would process that the parent node. So you would pop the parent node and update its values to its parent. So you would, as long as the stack is not empty, you would keep looping. So the way that would work though is you would break on, basically, as long as the index isn't the last child, then you would break. If the index is the last child, that's when you keep looping. So you can just have a while loop when the stack isn't empty. And so instead of an if statement here, you can make this a while loop, and then break out of the while loop on the index is anything other than if the index is the rightmost. Yeah, you break out of the loop if the index is anything other than the rightmost. How do I, a couple things here. Rightmost child. The index is not the rightmost child. Then you break. You can, yeah, that's kind of a weird thing with the while constructs. You can kind of set like a Boolean also. And just set that. It's either continue or not continue, something like that. But that's what would happen. Yeah, you'd have a potentially a whole sequence of kind of completions up the right side, for instance. Yeah, that's interesting. That's an interesting approach. The post-order traversal over an arbitrary branching factor over a tree, doing that iteratively. Very interesting. Very interesting. I think it's kind of expensive to do it that way though, but I think it's all right. As I said, you kind of have to each sub tree, you have to save the results in kind of an array to get completed eventually. Yeah, whereas you don't need to do the same thing with a pre-order traversal because you're processing that node immediately. By the way, this, what I'm showing you here with this array that you would have at each point, at each step, this post-order processing, this is how you perform a depth first search for the most part. That's basically what it achieves. It's the same thing as like if you had a recursive, you can pretty much take any recursive function and you can do the same thing here with a stack, and that'll give you an iterative version of the recursive solution. But I think, a post order, right? For the most part, that's what a post order is. What a recursive solution is. What's really tricky about this now, though, is one, I don't know why how they did it so fast. Some folks have like super fast solutions. That's one thing, and two, I don't know, man. I'm tempted to try to do what I would otherwise do recursively. I'm tempted to do it iteratively, like in interviews. And as you can tell, like it's taken me hours to kind of sort this one out, think this through. And it's one of those things where I don't think most employers, I don't think, are expecting you to do this stuff like iteratively on the spot during an interview. It's kind of a bit much. Oh yeah, it looks like when I serialize and deserialize the n-array tree, I'll be able to use this, but with, well, the pre-order again, you just need the index. You don't need the full. You could use the same serialization, same code, really. But yeah, this isn't as fast as I'd like to be. That's one thing, and two, I was kind of hoping doing it not recursively would make it faster, but didn't really seem to improve it very much. And then another thing is, yeah, the logic is involved. It's kind of a bit much to think about. It's not too bad, but it's not too bad. Like you can do iterative pre-order traversal using a stack. It's not too hard, and that could be easily adapted to more than just a binary tree and n-array trees. And then you could do the same thing. You post-order traversal with it through an n-array tree iteratively using a stack. That can also be done in a similar fashion that we have here, except like I mentioned, there'd be a while loop for when you complete sort of all the right subtrees. And arrays to kind of store the values and intermediary values. That's not too bad. I think the one thing that is tricky though is the Morris traversal using threaded binary trees. I think you can do that thread n-ary trees as well, and use Morris traversal, and that gives you an in order. The problem with that though is like you don't really know at what point, like an in order traversal, you kind of have a sense of when you're supposed to process the node, but an n-ary in order traversal, like, I guess can be like really complicated because you don't know where you're supposed to process the node. Like it could be in multiple spots that you're supposed to process the node in between. So I guess what you could do is, I guess you could still do a stack-based solution for, like this stack-based solution will handle, in order, post order, etc., pre-order. It'll handle any order, as long as you make the array large enough to handle the data that you need for the pre-processing, and then later the things that you need to have finished before you process the node. Now having like an arbitrary point in an n-ary solution that's not like an in-order traversal is kind of peculiar. It's actually a problem I've thought of when I was a kid, when I was younger. Not when I was a kid, but many years ago when I was at university. It's kind of interesting that I'm learning this now, or we're working on this now, is that this is a question I had when I was younger, was like, well, how can you do like an iterative version of, for instance, like the towers of Hanoi, I think tend to be solved recursively with an in-order traversal. Like how would you convert a recursive in-order traversal to an iterative stack-based iterative traversal, right? That would be either the Morris traversal, in order Morris traversal, or if you had multiple, if you made your towers of Hanoi more complicated and had multiple processes, recursive calls before the processing, and then recursive calls afterwards. That would be an example of what I was just describing, where you had an n-ary tree that you're going to recurse with an arbitrary order, not necessarily in order. Like obviously in order would be, it'd be in order traversal, but with a certain number of nodes to process before and nodes to process after the processing. I think you would use a post-order traversal like I'm describing here. However, the point at which you traverse would be different. Yeah, the point at which you traverse would be different. Instead of recursively traversing only on the final child, you would actually recursively traverse all part of the way through. Now, I guess one question is, you're not necessarily totally done with that child on the stack, or that yeah, I guess you would be. Actually, I guess you could pop all of these things from the stack. All of these parents. Yeah, once you've completed processing, all those parents can be cleared from the stack. You just have to make sure you jump to the correct next child, and I think that's fine. Yeah, I think you can pop those from the stack. Thinking about it, you would do that while loop, that post-processing while loop that you do would be No, no, I guess you wouldn't pop them from the stack. I think you still need to pop them only when you finish the last child, because so there's two parts then. There's processing the node to get the result, and then computing the result, and then, no, I think it's still a post-order traversal. It's just the update and the popping will just switch. So when you update, you update at a different point than when you pop. That's the only difference. Actually, that's the key. That would be the difference. It actually still would be the same post-order traversal. It's just you don't keep updating the data, the array, as you go through to the other children, but you still process the same way. Yeah. No, never mind. I take that back. That's interesting, but that's not actually. It's still a post-order traversal. It's just the computing that you do only uses part of the solution, partway through the solution, rather than all of the whole solution. In fact, you could still do the processing at the end. It's just you would only use part of the array and only save that result to the node above. Yeah, okay, that's actually not that complicated, not that special. It's the same thing as it's just another post order. So really, I guess all of these could be modeled as post order traversals, even the pre-order. The pre-order is probably the only one that you really can't write as a post order, but the in order and the post order both could be modeled with what I was just showing you before, the post order, stack-based post order. I think the pre-order traversal though is a little bit special, a little bit different. That I don't think you can do with the post order. I think it's just like totally different how it works. Okay, anyway, all right, I'm kind of rambling on about this. It's like really interesting. I don't know. It's very like it's very I wanted to also see like how slow my program runs. It's apparently a lot slower than some other people's other folks' setup. It's just really interesting because you might be wondering like how can you perform a depth first search iteratively, I guess, and not a breadth first search, but actually a depth first search. That's effectively what a pre-order post-order traversal would be very similar to that. Thought about that quite a bit. Like I said, I've seen quite a few different like questions that are sort of recursive type, iterative type, tree kind of traversal type questions, like many now. I'm realizing now, like most, if not all, programming problems you're going to see are some kind of loop or some kind of tree traversal. That's really it. That's really all you have with programming problems. Some kind of tree traversal, or some kind of array traversal. And that's pretty much all you have. These things are, I don't know how useful it is. Like again, in interviews, I don't think you're really going to be expected to go beyond like recursive solutions, but that you can use iterative stack-based solutions to replace your and actually you can in a lot of cases also replace your memoized solutions with dynamic programming solutions too, which is similar kind of has a similar kind of like there's this not dichotomy, but kind of not exchange or dichotomy, but there's this kind of like mapping from one to the other that you can do also. So pretty neat. Yeah, I don't know, man. When I was younger, I had this question about like how could you write a recursive function in general as an iterative function. I think you can in general write a recursive function as an iterative function. The only trick to it is that you need a stack. Yeah, that's kind of what it comes down to. But anyway, yeah. So thank you for watching. This has been interesting. This has been an adventure for me. It's been fun. I didn't think it was going to take this long. This ended up being more of like just a few more hours again, thinking about trees and recursion and iteration and the relationship of those things, which I spend a lot of time pondering and thinking about. Quite frankly, I have spent a lot of time, but I don't know. I've just seen many different problems that are kind of like they're interesting to ponder how you might change your approach. As far as like serialization and deserialization, this is an interesting question, interesting problem, but there are a few different ways to do it, and some of them better than others. I think the way I did it's not too bad. I think I probably use the same one for an array tree, same deal, almost exactly the same routine, except I think, yeah, pre-order. I would still do pre-order traversal. Although we would want to know what n is ahead of time instead of it being like totally arbitrary how many children there are. Actually, what we could do if you want to have a variable sized number of children, you can use colons for like children and then a semicolon for like the last child, I guess. Yeah, how did I do that? So how did I do it here? I said, yeah, so each child, it's going to be the root node, and the next node is, if it's null, it'll be empty. Yeah, and there's only 2 children per um, per node. And then what you can say is, if you see a semicolon, that demarcates a final child for a node. And so then you can use that to go back up the tree. So you don't necessarily need to know what n is ahead of time. If you know what n is ahead of time, you can use almost the same algorithm here. But if you don't know what n is, then you can just insert semicolons instead of commas, and you can use that to demarcate where the end of demarcate where the end of a node's children are. Where the end, demarcate the end of the children nodes of a node. There you go. And to demarcate the end of a node's children. There we go. Or the end of children nodes. End of a node's children. There you go. Got it. Okay, all right, I'm gonna stop here. So yeah, thanks for watching. I appreciate it. I think I'm gonna take a break, get some food, and then start another problem, I suppose. I don't know what I want to do exactly. I think I kind of want to just dive into another problem, but I also want to take a small break. I don't know. I might just pick up another problem. Yeah, thanks again for watching. Talk to you soon. Have a good rest of your day.